Hello students. Today I am available with a new topic related to a standard Brayton cycle for gases and numerical based on the Brayton cycle. Student, we know that gas turbine is one of the oldest device known to man for conversion of heat energy into mechanical work. The gas turbine is the most satisfactorily power development unit among the various means of producing mechanical power due to exceptional reliability, freedom from vibration, and ability to produce large power from units of comparatively very smaller size and weight. The gas turbine power plants nowadays is universally used as peak load plant, base load plant as well as standby unit due to its outstanding operational characteristic. So Brayton cycle is a theoretical cycle for simple open gas turbine power plant. This gas turbine power plant is widely used in aircraft as well as when we are talking on Earth. The closed cycle gas turbine power plant is used as a peak load plant, base load plant, or it is a standby unit, or it can be used with a nuclear power plant as a combined cycle power plant. So in this video we will discuss only about open cycle gas turbine power plant, where you will observe two constant pressure processes, that is two isobaric process as well as two isentropic process, that is two reversible adiabatic processes. So the simple open cycle gas turbine power plant consists of two isobaric process and two isentropic processes. So in case of open cycle gas turbine power plant, 1 to 2 process is isentropic compression of air, 2 to 3 process is the constant pressure heat addition process, 3 to 4 is isentropic expansion process, whereas 4 to 1 is a constant pressure energy rejection or constant pressure heat rejection process. So in next slide, the schematic diagram, PV diagram and TS diagram of open cycle gas turbine power plant is shown, and we have to discuss about that part. So now friend, you can see the schematic of open cycle gas turbine power plant with PV and TS diagram. So if we'll talk about open cycle gas turbine power plant, you find three major components are there. One is the rotary compressor, second is the combustion chamber, and third is a rotary turbine. If we'll talk about working of open cycle gas turbine power plant, you find that the air from the atmosphere that will enter into the compressor is a rotary compressor, which is a power consuming device. So the air will compressed, and at outlet of the compressor we will get high pressure, high temperature air. Now this high pressure, high temperature air is entered into the combustion chamber. So in the combustion chamber at constant pressure, the fuel is injected, that is high grade fuel is injected. Because of that, the high pressure, high temperature air is available and fuel is injected. So the fuel will catch the fire, and in presence of air, the flame will generate and that will propagate. Because of that, exhaust gases will be generated. These exhaust gases are available at very high temperature, and these exhaust gases are entered into the rotary turbine. Now in the rotary turbine, the gas will expand. It will rotate the blade of the turbine, and because of that, the power is available or work is available from the turbine, and that will be supplied to the system. And at the end, the exhaust gases will be thrown to the surrounding. So here you will see the cycle is open. So here the air is working as a working substance that will enter into the system, and exhaust gases will be thrown to the surrounding. So actually the process 4 to 1, which you will see in the PV diagram as well as TS diagram, that is not actually available because it is an open cycle gas turbine power plant. Air is sucked and exhaust gases are thrown. In the schematic diagram, you can see compressor and turbine are connected with the common shaft. It means that to run the compressor, the power is supplied from the turbine. And actually, out of the total power generated by the turbine, two-third amount of power is consumed to run the compressor. So only one-third amount of power is available to run the system and its all auxiliaries and accessories. Because of that, we can find the efficiency of open cycle gas turbine power plant is very less, that is less than 25% approximately. So if we want to improve the efficiency of simple open cycle gas turbine power plant, we have to go for different methods like reheating, regeneration, intercooling, or combination of all these things and other methods to improve the efficiency. So at present in this video we will discuss only about simple open cycle gas turbine power plant working, the representation of the same on the PS, a PV and TS diagram and numerical based on that. Now our first task is to find out efficiency of simple open cycle gas turbine power plant. So we know that generally efficiency is a ratio of net work available divided by supplied heat. Or in other terms, you can say efficiency is a ratio of heat added minus heat rejected divided by heat added. So if you refer the previous TS diagram, you can find out the amount of heat added, that is MCP T3 minus T2, heat rejected, that is MCP T4 minus T1, means the heat addition takes place in the combustion chamber and the heat rejection takes place in the atmosphere where exhaust gases will enter into the atmosphere. So MCP T3 minus T2, that is heat addition at constant pressure in the combustion chamber, whereas at constant pressure heat is rejected by means of exhaust gas enter into the surrounding, that is MCP T4 minus T1, where M is the mass of gas or air, Cp is the specific heat at constant pressure for air or gas. If we assume that mass of air or gas is same and Cp of air or gas is same, in that case we will get efficiency that is equals to 1 minus T4 minus T1 divided by T3 minus T2. Again, if we'll go for further simplification, we will get efficiency that is equals to 1 minus T1 into bracket T4 minus T1 divided by T2 into bracket T3 minus T2 minus 1, whereas P2 by P1 is a pressure ratio. We know the relationship between temperature and pressure, that is T2 by T1, that is equals to P2 by P1 raised to gamma minus 1, and if we are telling that P2 by P1 is the pressure ratio, then we can say that T2 by T1 that is equals to pressure ratio raised to gamma minus 1 divided by gamma, where gamma is adiabatic index and for air the value of gamma is equals to 1.4. So now P3 by P4 that is again equals to P2 by P1, that is a pressure ratio, or you can say T3 by T4 that is equals to T2 by T1, or you can tell that upon rearranging T3 by T2 that is equals to T4 by T1, and because of that you can say the efficiency that is equals to 1 minus 1 upon Rp, that is pressure ratio raised to gamma minus 1 upon gamma. So from this equation we can conclude that efficiency of Brayton cycle is depend upon only two parameters, that is pressure ratio and adiabatic index gamma. So if there is a variation in gamma or if there is a variation in pressure ratio, efficiency of Brayton cycle will vary. Now, we try to find out what is the relationship between efficiency and pressure ratio for simple open cycle gas turbine power plant. So you can see the graph of efficiency versus pressure ratio for open cycle gas turbine power plant. So here you can find that when there is rise in the pressure ratio, the efficiency of simple open cycle gas turbine power plant is increasing. Means you can say that when the pressure ratio is go on increasing, the efficiency is go on increasing. But definitely one important thing which you have to see in the graph is the efficiency is not going beyond 60%. In no case the efficiency is go beyond 60% for simple open cycle gas turbine power plant, even though the pressure ratio is go on increasing and increasing. So now we have to find out what is the network available from the system, and then we will conclude something. So as we had discussed in the previous theory that out of the total power generated by the turbine, or you can say out of the total work available from the turbine, maximum amount of work is supplied, or you can say two-third amount of work is supplied to run the compressor. So this kind of question may be asked to you in your competitive examination or in your university examination. So our first task is to find out what is the network available with the system, because compressor is a power consuming device. So to run the compressor, power is required. So we had discussed in the previous slide that the turbine and compressor both are mounted on the common shaft. So here we find that net work available, that is equals to turbine work minus compression work, and that is equals to H3 minus H4 minus H2 minus H1. Or you can write that is equals to Cp into T3 minus T4 minus Cp into T2 minus T1, where we are assuming that mass of air that is equals to mass of gas. And based on that we can find that T2 by T1 that is equals to pressure ratio raised to gamma minus 1 upon gamma, and T3 by T4 that is equals to P3 by P4 raised to gamma minus 1 upon gamma, and we know that P2 by P1 that is equals to, you can say, P3 by P4, and that is equals to pressure ratio, whereas this T2 by T1 that is equals to T3 by T4. So what we have to do is network that is equals to Cp. From the first part we will keep T3 common, that is the highest temperature of the cycle, and from the second part we will keep T1 constant, that is the lowest temperature of the cycle. So we will get the equation that is network that is equals to Cp into T3 into bracket 1 minus T4 by T3 bracket complete minus Cp into T1. T1 is the lowest temperature of the cycle into bracket T2 divided by T1 minus 1. And now we are replacing T4 by T3 and T2 by T1 by pressure ratio. So we will get network that is equals to Cp into T3 into square bracket 1 minus 1 upon Rp raised to gamma minus 1 upon gamma minus Cp into T1 into square bracket pressure ratio raised to gamma minus 1 upon gamma minus 1 bracket is completed. So in this equation you will observe that the network is depend only upon pressure ratio. Otherwise, for a one particular fluid, gamma is constant, minimum cycle temperature is fixed, and maximum cycle temperature is also fixed, because the minimum cycle temperature is depend upon surrounding, that is atmosphere. Maximum cycle temperature is fixed because of the metallurgical limits of the material which we are using in the gas turbine power plant. Otherwise, at very high temperature, that material may melt and it will damage the system. Lower temperature and higher temperature we cannot control. Lower temperature is surrounding temperature and higher temperature is because of the metallurgical limits. So now the network of the system is depend only upon pressure ratio. So now our task is to find out what is the value of pressure ratio for which we will get maximum work output. Again I am repeating, our task is to find out the pressure ratio for which net work available from the turbine is maximum. So the exercise which you can see now is to find out what is the value of optimum pressure ratio for which net work available is maximum. So we have to find out what is that value. So what we have to do is we have to differentiate net work done with respect to pressure ratio and we have to equate it with 0. So we have to go for d by drp of w net and that we have to equate it with 0. So you find all the steps are mentioned here for the derivation, that is dw net by drp that is equals to 0, and from that we will get T3 into pressure ratio raised to minus 2 into gamma minus 1 divided by gamma that is equals to T1 into pressure ratio raised to 1 upon gamma. So pressure ratio raised to minus into 2 gamma plus 1 divided by gamma that is equals to T1 by T3. So you can say that Rp, that is pressure ratio raised to minus 2 into bracket gamma minus 1 bracket complete divided by gamma that is equals to T1 upon T3, or you can say T1 upon T3 that is equals to 1 upon pressure ratio raised to 2 minus gamma divided by gamma, or you can say that pressure ratio that is equals to T3 by T1 raised to gamma upon 2 into gamma minus 1. It means that here the pressure ratio, that is optimum one, that is ratio of T3 that is the maximum temperature of the cycle divided by T1 that is the minimum temperature of the cycle raised to gamma that is adiabatic index divided by 2 into gamma minus 1. So this is the value of optimum pressure ratio for which maximum work done is available. So if we'll put the optimum value of pressure ratio in this equation of net work done, we'll get maximum net work available for open cycle gas turbine power plant with the optimum pressure ratio of T3 by T1 raised to gamma upon 2 into gamma minus 1. So now friend, we have to solve simple numerical related to open cycle gas turbine power plant. But before we will discuss about the simple numerical, one very important question that may be asked or you must know for the open cycle gas turbine power plant is, generally it is asked like that, high air fuel ratio and low pressure ratio is a special characteristic of open cycle gas turbine power plant. Justify. So generally in case of open cycle gas turbine power plant compared to Otto cycle and diesel cycle, the air fuel ratio is very high, that is 100 is to 1. If we talk about petrol engine, it is 15 is to 1. If we talk about diesel engine, you can say it is 20 is to 1. But for gas turbine power plant, it is 100 is to 1. So air fuel ratio is very high and the pressure ratio is low. So that is a special characteristic of gas turbine power plant. You try to find out why it is so. Definitely you will get the answer based on the theory which we had discussed in the previous slides. So now we will discuss the simple numerical related to simple open cycle gas turbine power plant. So in the data it is given that in a gas turbine power plant working on Brayton cycle, Air enters the compressor at 1 bar and 293 Kelvin and compress up to 3.5 bar. If the temperature at the turbine inlet is 873 Kelvin, determine cycle efficiency, heat supplied per kg of air, net work available per kg of air, heat rejected per kg of air, and temperature of air at turbine inlet. So based on the previous theory what we had discussed, we have to solve the numerical, but very important thing which you can see here is mass of air is given 1 kg and we have to assume that mass of air that is equals to mass of gas. And now we have to solve this simple problem. Data it is given that P1 that is initial pressure is 1 bar, initial temperature is 293 Kelvin, pressure ratio is given 3.5, that because the final pressure is given 3.5 bar, so pressure ratio is P2 by P1, that is 3.5 divided by 1, so it is 3.5, so pressure ratio is 3.5. T3 that is highest temperature of cycle is 873 Kelvin. So the first task is to find out cycle efficiency, but before that you can see the same cycle is represented on the PV diagram and that is shown. So now our first task is to find out efficiency. So efficiency that is equals to 1 minus 1 upon pressure ratio raised to gamma minus 1 upon gamma. The gamma for air is 1.4 and pressure ratio is 3.5 bar divided by 1 bar, that is 3.5. So we will get efficiency that is equals to 1 minus 1 upon 3.5 raised to 1.4 minus 1 divided by 1.4. So efficiency value which you can see is 30%. If you refer the numerical related to Otto cycle or diesel cycle, you will observe that efficiency is always more than 50%. Or if we talk about Otto cycle, diesel cycle, Rankine cycle, efficiency in all that case is more than 50%, and particularly for Otto cycle and diesel cycle the efficiency is more than 70, 80, 90%. But here you can find the efficiency of simple open cycle gas turbine power plant is around 30% only. So we have to go for different methods to improve the efficiency of simple open cycle gas turbine power plant. Now we have to discuss about our next task. Now the second task is to find out heat supplied per kg of air. So to find out that, when we have to solve any numerical related to a standard cycle, we had discussed that first of all we have to find out what is the value of all the pressures and what is the value of all the temperatures. Here the working substance is air or gas, so there is no need to talk about steam table or any property table. Just we have to use the relationship between P, V and T, and based on that we have to solve the numerical. So for the process 1 to 2, that is the compression process, we know that T2 that is equals to T1 into pressure ratio raised to gamma minus 1 upon gamma. So T1 is 293 Kelvin. So T2 is 293 into 3.5 raised to 1.4 minus 1 divided by 1.4. So we'll get the T2 temperature, that is 419 Kelvin. So now heat supplied, that is equals to Q1 and that is equals to Cp, or you can say mCp T3 minus T2. M is the mass of air or gas, that is 1 kg given in the data. T3 is the highest temperature of cycle, that is 873 Kelvin, and T2 which we had calculated. So heat supplied Q1 that is equals to 1.005, that is Cp of air which we have to remember, 1.005 kilojoule per kilogram Kelvin into 873 minus 419. So heat supplied Q1 that is equals to 456.27 kilojoule per kilogram. Now the next task is net work available. We know that efficiency that is equals to net work available divided by heat supplied. So efficiency is calculated, and also we had calculated what is the amount of heat supply. So based on that, directly we can calculate what is the net work available. Otherwise, we have to find out what is turbine work, what is compression work, and when we'll go for turbine work minus compression work, we will get net work available. So we can go for that method also. But here we are approaching with a simple part, that is the network, that is equals to efficiency into supplied heat. So efficiency is known to us, that is 30%, that is 0.3 into Q1, that is 456.27. So the network available is 136.88 kilojoule per kilogram. Now the next task is to find out heat rejected per kg of air. So the net work available, that is heat supplied minus heat rejected. So heat rejected, that is equals to Q1 minus net work available, that is 456.27 minus 136.88, that is net heat rejected per kg of air, that is equals to 319.39 kilojoule per kilogram. And the last task is to find out air temperature at turbine outlet. So for the process 3 to 4, we know that T4, that is equals to T3 into P4 by P3 raised to gamma minus 1 upon gamma. That is the relationship between temperature and pressure. We know T3 is the highest temperature of cycle, that is 873, and P4 by P3, that is inverse of pressure ratio. So that is 1 upon 3.5 raised to 1.4 minus 1 divided by 1.4. So that T4 value, that is equals to 610.5 Kelvin. So you can see all the temperatures T1, T2, T3 and T4, all temperatures are available. We know all the pressures. So based on the available pressure and temperature, we can also find out what is the heat supplied, heat rejected, net work available based on these pressures and temperatures. So you can, if you want, you can again solve the numerical with help of finding out all the pressures and temperature initially, and based on that values you can calculate what is the net work available and what is heat rejected part. So friends, in this video we had discussed about a standard Brayton cycle, that is we had discussed about simple open cycle gas turbine power plant, where we had discussed in general about what are the components of simple open cycle gas turbine power plant, what is the working of simple open cycle gas turbine power plant, representation of the Brayton cycle on PV and TS diagram. Also, we had find out efficiency of Brayton cycle, what is the net work done available from the cycle, what is the optimum pressure ratio for the Brayton cycle, and based on that we can calculate what is the maximum net work available from the simple open cycle gas turbine power plant. Based on that, we had go for one simple numerical related to Brayton cycle, in which we had concluded that efficiency of simple open cycle gas turbine power plant is less. So if we want to use this cycle as a standby unit or as a base load plant or as a peak load plant, we have to go for some modification into the cycle, and that is various methods to improve the efficiency of open cycle gas turbine power plant, that is reheating, regeneration, intercooling and combination of all these things. So if you like this if you like this lecture, if you like this video, then do not forget to share this channel, like this video, and do not forget to subscribe this channel. Thank you. Have a nice day. Goodbye.